All right. All right, so I'm going to rehash a little bit of what we did right before spring break about sine waves, and we're going to go a little bit deeper today than we did then, kind of talking about applications of AC stuff, and talk about a particularly important concept called phasors that we use pretty often in AC circuits. Okay, so when we met last time, we talked about this DC versus AC. Yes, DC means direct current, AC means alternating current. If you had to describe what does a DC waveform look like, right? So if I showed voltage versus time or current versus time, what does a DC waveform look like?
Be a constant value.
Yeah, it'd be a constant value, okay? If I had AC, and let's say I had, I guess this circuit here, let's say I have an AC circuit, about the simplest AC circuit I could think of. What would the current look like in that circuit?
Like a sinusoidal wave?
Yeah, and yeah, in general, what you say for an AC circuit, it means it's alternating. So it could be sinusoidal, could be a square wave.
Squared.
Yeah. Eli, how did your meeting go with Daniel? I can ask you that later.
Okay.
Hopefully it went well.
It did.
Okay, good. All right. So AC can mean any, can mean basically what it says is I have a waveform that is non-constant. All right. And it doesn't mean just current. The voltage could look like this as well, right? In fact, if the voltage is sinusoidal, the currents are going to be sinusoidal. So part of the reason why we call that alternating current is because if I said the current is going this way, the fact that the current goes positive and then negative, what does that mean?
It's reversing.
It's reversing. So that means that charges are basically going this way and that way and this way and that way. They're basically sloshing back and forth. That's part of the reason why we always say, you know what, the signs aren't really all that important. That we keep track of the signs is important. In an AC circuit, the sign is always kind of a funny thing to think about. Okay. Now, what I talked about last time, so this is AC, this guy down here, the square wave. So is this, right? The sine wave. One thing that, if you guys know, and you haven't gotten to this yet in 2254, but if I have a square wave like I have there at the bottom, one thing some of you guys probably know, and I mentioned it last time, if I have a square wave like I have at the bottom, one thing that's true about any periodic waveform is I can use the Fourier series idea. So anybody know what a Fourier series is?
You can approximate curves using sums of sines and cosines.
Yeah, I can approximate curves using sums of sines and cosines. So basically what that means is I can think of a square wave as a bunch of sine waves, all right? And so basically sine waves have a really special place in our analysis of circuits. And if we do that, as we'll see here today, we can make some simplifications that as we go through today and Wednesday, we'll see that we're going to be able to make some simplifications to the way we do analysis, make them similar to the way that we looked at DC circuits. Okay. All right. So I talked last time, I like to look at this as sort of an example, right? Where I have a DC to AC inverter, right? An inverter is a circuit that goes from a DC value to an AC value. And that happens in lots of different places. It's very, very common to go from DC to AC. Anymore, almost anything goes from DC to AC at some level. Like your computer has that. There's all sorts of stuff like this. But in this example, if I have a photovoltaic array, a solar panel, right? A solar panel is a DC output. If you look at the output voltage on a solar panel, the voltage basically goes up or down based on how much sun is shining on that device. So just as an example here, if I have the DC waveform, this, the voltage across this capacitor right here is this yellow waveform. And the output in this case, the grid on this side, this is the grid, okay, quote unquote, all right. So that is a sinusoidal waveform. That's the green right there. So we have a couple of terms that we use to talk about the grid, okay? So in the US, what's the frequency of the grid?
60 hertz.
60 hertz, okay, 60 hertz. and that is frequency F. We're going to talk about this in a minute. But that says, so if I have a 60 hertz waveform, how many periods does that waveform have in 1 second?
1/60.
Well, 1/60 is the period. That's how long a period.
That's 60 periods per
60 periods. Yeah. So the older way to say that is also, sometimes people will say 60 cycles per second. All right. 60 periods per second. All right. That means it goes through its period 60 times every second. All right. So in this case, what I have is a couple of different types of AC waveforms. Like this waveform here, that yellow waveform, if you look at it, it's tough to really see what's going on, but there's a super fast square wave inside there. In this case, that square wave is probably on the order of about 50 kilohertz. All right. So 50 kilohertz means how many periods in a second?
50,000.
50,000. Okay. That's what the voltage V sub S looks like coming out of this thing. And then I put it through this thing called a filter. And some of you guys have probably heard of a filter before. That's something we're going to talk about later this semester. But a filter basically takes as its input this yellow waveform, which is AC, and it outputs for me the green. All right. So looking at that, if I had a 50 kilohertz waveform, kind of ugly looking thing going in here, and then I have this green thing coming out, what does it look like the filter did?
It mirrors it.
Took some noise out.
It gets the noise out, basically gets the high frequency stuff out of there. All right. So it removes certain frequencies and keeps other frequencies. All right. So we're going to learn a lot more about that concept as we go through the semester. But I mean, I think it's kind of important to sort of bear in mind, okay, this, going from DC to AC is a pretty common thing to do. Now, DC circuits are pretty boring circuits, right? In general, they, if I have resistors, then they don't do much that's very exciting. The most common place where we have DC circuits is what? I'll ask this guy. So so DC circuit?
Batteries.
Batteries are a DC source, right? All digital circuits are really DC circuits, right? All the voltages that you have in DC circuits, like ones and zeros, we say a 0 is 0 volts, a 1 might be 5 volts, all right, depending on the type of logic that you're working with. So constant voltages happen in digital circuits all the time. But AC waveforms happen pretty commonly. And I mentioned this last time, right? So I talked about the fact that sine waves have a really special place in general when we're talking about any kind of analysis of an electrical engineering problem. So radio waves, I said, were one example. And, what I said is if I'm looking at, in this case, I just showed, AM and FM. And that's not just necessarily just for radio, like AM and FM radio. If you look at the waveform coming out of your cell phone, for instance, that's an AM modulated waveform. All right. So in other words, it's amplitude modulated. But basically what it says is here, right, is these guys are pretty common. Essentially, if I'm talking about a radio station, let's say this guy is 98.5 megahertz. All right. So if I said 98.5 megahertz, how many periods does that have in a second?
So it's 98,500 per second.
No,
Oh, it's times 6. It's times
98
6,
million.
not times 3. Yeah.
98 million, right?
Yeah.
So, if I had a 1 gigahertz clock, that means a 1 gigahertz waveform goes through 1 billion cycles in 1 second. Okay, very fast, obviously. But, these AC or sinusoidal waveforms in particular are pretty common. So we're launching these waves all the time from antennas and receiving them on antennas. So your cell phone is receiving 2.4 gigahertz sine waves all the time, right, on the Wi-Fi network and things like that. And I also mentioned last time audio waves, right? So in fact, I think one of the things that I did, and I'm going to take a quick look here at my phone. I think I showed this last time, right? So I think you guys can see that as I guess it doesn't turn. All right, so as I talk, you can see on the screen there on my phone that you see different types of waveforms, and the vertical values kind of change as I talk, because as I talk, depending on what I'm saying, it's louder or softer. But if I were to just try to do a single tone, like I think if I just me see. All right, I don't know if that's going to work, but you can kind of see if I try to do sort of a single tone, you get sort of a sine wave. All right, essentially a single note, right, is effectively a sine wave. And if I'm basically saying a bunch of stuff, then what happens is I get a bunch of sine waves added together. So audio is pretty common. Audio is one example of this. Power is another example. All right, so basically we get all sorts of examples of where we see sinusoids, and those sinusoids need to be processed by our circuits. And so it's really important for us to kind of focus in on those, right? Power, I said, is the other example. All of the big rotating iron generators out there in the world basically produce sinusoidal output voltages. We need to know how to deal with these things, and we have some special tricks for dealing with them. And usually if we have more complicated waves, like this guy I said right here, right, which is a very complicated waveform, I can usually still think of him as a sum of sine waves, right? Which means that we can always go back to this type of analysis. All right. So last time we introduced some basic concepts. All right. And I'm going to go back and I want to review those real quick, but some things that you really kind of know from trigonometry that we need to kind of go back to. All right. Which is, so the sine function. So I've got sine drawn there on the screen. All right. Sine, by its very definition, is periodic in 2 pi radians. In other words, if I look at the function sine of theta, all right, so what I've got here is, this is sine of theta. Oops. This guy is sine of theta. He's periodic in 2 pi radians, which means after 2 pi radians, he repeats. Okay. What if I were to draw cosine here? What would cosine look like? What's the difference?
Shifted by 90 degrees.
Shifted by 90 degrees. And which direction shifted?
Left.
To the left.
To the left. All right, so cosine would look like that. Now, it's not the greatest, but you get the idea. All right, this guy here is cosine. All right. Now, one of the important things that we talk about in sort of the electrical engineering context is we don't look at things typically as a function of angle. All right. Sine is by definition a function of angle. We typically talk about it as a function of time. All right. In other words, I apply, like if you think about the voltage that you get at the wall outlet, that voltage has a frequency of 60 hertz, which means that it's repeating 60 times every second. And it's going through 2 pi radians 60 times every second. So what we really talk about is sinusoidal functions of time, right? So I wrote this out as x of t. All right, x of t means that the sine is changing as a function of time. So in this case, what I'm saying is the angle is changing as a function of time. So theta equals omega t. All right. So if by definition theta has units of radians and time has units of seconds, right? What must be the default value of this value omega here? The rate at which the angle changes. What are the units on that guy?
Radians over seconds.
Yeah, radians per second. All right. That's the rate at which the angle of that sine wave is changing. Okay. So omega t, right? And so this would be important. Omega t is always in radians per second, is that omega. All right. So a couple of further definitions to this guy, right? Is, yeah, sure, sine looks like what I've got there on the top, right? As you learned it, sine of theta, that's what's up here. All right, x m sine theta. In reality, what we look at is this guy on the bottom, which is xm sine of omega t. We look at it as a function of time. So we always plot time on our x-axis. Almost always you see time on your x-axis for any engineering problem, because we're talking about sinusoidal waveforms, sinusoids that are functions of time. All right, so this value x sub m here, what do we call that?
X.
Amplitude.
Amplitude. All right. Basically, it's the peak value of that waveform. So in other words, if I look at the peak of this guy, the peak right, is always going to be whatever the amplitude is, because sine, by definition, how big is sine? What's the maximum value on sine?
1.
1,
One.
right? Yeah, it's always the case that if I look at sine, right, sine of theta is always stuck between 1 and -1, and I'd be careful like that. It's always stuck between -1 and 1. All right, if I have anything bigger than that, I say I have an amplitude to this thing. All right, so a couple of things then. If I look at sine as I go through a period, right, and this is stuff you guys hopefully largely know, right? But if I look at this as I go through one period, right here, sine starts at 0, reaches a peak at pi over 2. What we say is that that is essentially at time t over 4, where I call t the period, okay? And then at half the period, t over 2, he's back at 0. At 3/4 of the period, he's here, and at a period, he's all the way back to where he started, okay? So, this is typically what we look for. In other words, if I'm looking on an oscilloscope, which we'll do here later today, right? If I look on an oscilloscope at a waveform, what I see is something that's a function of time, not a function of angle. All right. So looking at these guys right here, right? You should be able to sort of see how would I relate angle to time, right? I see that theta equals omega t, like that, right? So let's say I wanted to figure out how omega relates to the period, right? How could I figure that out? How omega relates to one period based on what I have right there? How could I figure that out?
2 pi times the frequency.
Well, so 2 pi times the frequency is how it, but if I look at this, so at time t equal to 0, all right? So just to make sure we understand here, so at t equal to 0, let's say t and theta, at t equal to 0, what's the angle?
0.
0.
Zero.
All right, let me jump ahead. At 2 pi, what's the value of t at 2 pi?
Also 0.
See, that's why I wanted to ask that question.
2 pi over omega.
Of W of omega.
No, it's capital T. At time capital T, the angle is equal to 2 pi. All right, and it's going to be equal to 4 pi at what time?
2t.
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 And t in this case is 2 pi over omega.
T is the period. All right, that's the thing I want to be clear about, right? So somebody just said that, but basically if I look at this, right, 2 pi equals omega times capital T. At time t, the angle is equal to 2 pi. So that means that omega is equal to 2 pi over capital T, right? That's where that comes from. The fact that every time I go through a period, I've basically gone through 2 pi radians. So when I go through 2 periods, I've gone through 4 pi. When I've gone through 3 periods, I've gone through 6 pi, right? It just keeps repeating like that. All right. So we get this relationship here that omega equals 2 pi over t. Now, what you'll see in a lot of our problems as we go through is I'm going to give you period or angular frequency, and you're going to have to do some kind of a conversion, usually back and forth between them. All right. Now, typically, we don't talk in terms of period or angular frequency, right? What do we use more commonly to define the timing of these waveforms? I've already said it once.
Would it be phase?
Not the phase. So I talked about the power grid having a particular frequency, right? We said that was 60 hertz. Most of the time, engineers don't talk about the timing in terms of time or angular frequency, but they talk about it in terms of just what we call frequency. All right, so we have our definitions here. So angular frequency, frequency, period, and amplitude, right? So period has units of seconds, okay? frequency has units of hertz, angular frequency has radians per second, all right? And we relate essentially here, all right, we relate the angular frequency to frequency by noting that omega is equal to 2 pi f, right? So, and we also said that omega was equal to 2 pi over t, like that, all right? So that gives me a couple of relationships there that I see. So the period is 1 over the frequency. So if I said, all right, I have f is 60 hertz, what's the period of that waveform if f is 60 hertz?
1 over
It's
60.
60 cycles per
125.
second.
Yeah, 1 over 60. So 60 hertz means I could also say that as 60 cycles per second. All right, or 60 periods in a second. One cycle and one period, those are kind of used interchangeably. So that means a period is 1 over 60 seconds, which if you do the math on that works out to about 16.67 seconds. All right. Okay, so important to kind of bear those ideas in mind. Everything you need to usually relate them is on this slide, and you're covering that probably also a little bit in 2254 as well. All right.
Wait, why is it 16.67 instead of 0.0167? Like, why is it?
Milliseconds.
Oh, okay.
Yeah, that's what it is. Sorry. And when you did that calculation, you may say that it's 16.6 bar, right? Because it should be 16.666666. I think it's probably what you're asking, Christian.
Yeah, okay. When
And
you
my
said
units are wrong.
milliseconds, when you said milliseconds, it cleared it up 100%.
And my units were one point I wanted to make. So yes, it's milliseconds. I didn't put 6 with a bar over it because, just to be clear, no real engineer ever does that. Okay, they always round off to some point. And so there's a couple of things. You'll never see me put a bar over something like that because that implies incredible accuracy that you don't have in the real world, right? So we typically do 16.67 milliseconds like that. All right, and I'll round it up a little bit. Okay. All right. So a couple of definitions then, and just to, what we typically see when I'm talking about a waveform in any kind of electrical computer engineering problem is I usually have it in the form that I have right here. X of t is some amplitude times cosine omega t plus phi. And I specifically just said cosine omega t plus phi as opposed to sine. All right. And we're going to see why we do that. But basically, we make a definition that we sort of reference all the waveforms that we get. We define them relative to cosine. All right. And you'll talk more about why that is in 2254 and in 3111. But for now, I basically see that that's the reference framework that we use, and we're going to work with it. All right. In this class, I'm not going to waste our time too much in talking about the details of the math. I'm going to focus much more on how we apply the math. Okay. So we're going to use that framework to define our waveforms. All right. And so there's basically, as I've defined it here on the slide, there's 3 key parameters that are in that. So I say parameters, basically like 3 sets of numbers that I need to know to be able to sketch that waveform. Like in other words, the sketch that I showed over here, right, on this axis here, the sketch that I showed, in order to be able to draw that sketch versus time, right? So I'm plotting here. This is my x of t, and this is my t here, right? I need to know the amplitude, right? That's xm. I need to know something about how fast it varies. So in other words, I need to know something about the frequency f, the period t, or the angular frequency omega. And then we have this other piece that we call the phase shift phi, all right, which tells us how offset the waveform is from being a cosine at t equal to 0, okay? So just to be clear, if I'm looking at this guy right here, the waveform that I've shown here on the right side of the slide, is this guy cosine? What I've drawn there?
Yes, seems like it.
Yeah, it's not starting at 0, so I'd call it cosine.
But it doesn't start at its max either.
It doesn't start at its max. So t equal to 0 is right here. Okay. So t equal to 0, this guy is not at its maximum. All right, so let's just see if we can define a couple of things based on what we see right here. So let me just based on what I got on the screen. Let's say I wanted to figure out what the function was for this guy. So what's the amplitude of what I've shown here on the screen?
10.
10.
N.
Okay. All right. So I can say that this guy is x of t equal to 10 cosine of something. Okay. Now, how can I figure out what this omega is? Look at this picture. How could I figure out the omega? What would be the way to figure that out from this picture?
So we need to figure out a t.
Yeah, I need something to figure out the timing, right? And so we know that this guy repeats every period. Okay. So how can I look at this and figure out what the period is?
Take a look at two
Oh,
peaks
okay.
and then just subtract it.
Take a look at two peaks, right? So I see I've got a peak here and I got a peak here. All right. Now I can kind of eyeball that. If you look at that carefully right there, how much time does it look like passes between the peak here on the left and the peak on the right?
Why don't
0.10.
0.1 seconds. So it looks like t here is 0.1 seconds. Okay. So what's f? The
1
frequency,
second? 1.
1 over 0.1.
which is
1.
how many hertz?
10.
10 hertz. Okay. So that means this guy I'd write as 20 pi t. Okay. Omega equals 2 pi times 10. Okay. So 20 pi t. Now he's not quite cosine, right? Not quite cosine. So what else do I need? I have this plus phi that goes in here. How can I figure that out?
This is setting the time as 0 with the initial value.
Yeah, I could basically figure out, okay, well, it looks like this guy is about 7 at time t equal to 0, right? So I could use that value. I could say, well, that means that if I mean, let's just say it's 7, right? I could say that I have 7 equals, I can't, 7 equals x of 0, and that's equal to 10 cosine of phi, and then I could figure out what phi is. All right. Now, one question is we can go through and solve that, but just looking at this, is that phi going to be negative or positive? Anybody know?
It'd be positive since it's shifted to the left, right?
Be positive since it's shifted to the left. Okay, so a couple of things here. Let's before I go on, I want to look at this definition. So I took this straight from Zybooks here, right? So if I look at any waveform, so we define everything. So it says here, V2 of t. This is our reference wave with phi equal to 0, meaning that this guy here would be Vm cosine omega t. Okay, his phi is equal to 0. This particular guy here, right, V1 has his peak a little bit later, and just so happens to have his peak apparently pi over 4 radians later. If I shift something forward in, well, I guess I just want to be clear about this. I'm shifting this backward in time. All right, I'm going to try to explain what that means, but I'm shifting, when I shift something over to the right like this. So if I took cosine and I shifted it to the right like that, then that means that this waveform here, we say that it lags that first waveform. It lags V2. And we say this green one here leads that waveform. In other words, leading in this case, what I mean to say in this is if I look at all three of these waveforms essentially are cosinusoidal waveforms, right? What I'm saying is the one that leads has its peak a little bit earlier, right? A time a negative time happens before time t equal to 0, right? A positive time happens after t equal to 0. So if it's leading, that means that it happens earlier in time, okay? So we use these terms leading and lagging, right? So if I had to sketch out what these guys are, right? So I said that V2 of t, I guess let's just be clear. I'll write them all down here. So this guy's V1 of t, or well, it's V3 of t, I guess, according to what this says. V3 of t is Vm cosine, and it says omega t plus pi over 4. This guy leads by pi over 4. All right. V2 here, this guy would just basically be simply Vm cosine omega t. And then I guess V1, the red waveform, how would I write that one?
Minus pi over 4.
Yeah, minus pi over 4. All right. This is not the most exciting stuff in the world, but it's important. All right. So basically what that says, the way I think about this is the red one is lagging the blue one. The green one is leading. And the term basically says that if I just think of everything as a cosine, his peak of the green one happened earlier, right? So it's leading, it happens earlier in time, whereas this guy's lagging, it happens later in time. All right, and we use those terms a lot, especially when we start talking about things in power, which we'll do later in the semester. All right, so let's do kind of a quick example here. I want to define a function for this guy. So in other words, I want to get this in the function. This is v of t, and this guy is Vm cosine omega t plus phi. I want to figure out all of the components that go with that. Okay. All right. So help me out with that. How would I do this? Where should I start?
Finding the amplitude.
Yeah. Okay. So looking at this, apparently the peak happens at 1.2 milliseconds. Okay. So what's the amplitude?
10.
Yeah, 10. All right. Very simple. All right. How do I then figure out what omega is from this?
We can take the 6.2 and 26.2.
Yep. Okay. So basically the difference between, so I know this guy repeats. He goes through 0 apparently at 6.2, and then he goes through 0 again at 26.2.
So it'll be 20 millisecond. So it'll be 2 pi 20 millisecond.
Almost, right? So this guy is, so this is milliseconds. So this is 20 milliseconds.
And you want to convert that into
And so if I to convert that
frequency.
to omega, so let's do it a couple of steps, right? How do I relate that to f? F is what?
1 over t.
1 over t. So 1 over 20 milliseconds works out to be 50 hertz. If I compute that. And my omega works out to be what?
2 pi times
2
50.
pi 50.
2 pi f, yeah. So 2 pi 50, so 100 pi, which if I wanted to get a number for that, that's basically 314. What are my units here?
Radians.
Radians per second.
Radians per second. Okay. All right, now, so we got everything. What about phi? How do I figure out the phi here? So I'm doing it relative to cosine. So cosine would have its peak at time t equal to 0. Okay. What time
Well,
does
it
this
looks
guy
like-
have its peak?
Looks like this is lagging by 1.2 milliseconds.
Yep. Yeah, this guy lags by 1.2 milliseconds. Okay. So the way I'm going to look at this, there's a couple of ways of doing it. I'm going to say, well, this guy looks like relative to cosine, and cosine would be, basically having its peak right here. The time delay there looks like it's 1.2 milliseconds. How do I relate 1.2 milliseconds to an angle? How much of an angle does that
Would you
mean?
multiply it by the angular frequency?
Yep, that's exactly right. So in other words, the phi value here, the angle would be omega times delta t. Okay, omega times delta t. So what is that? That's 2 pi over 20, right? times delta t is 1.2 milliseconds. I should be careful. That's 2 pi over 20 milliseconds, right? Times 1.2 milliseconds. Now, I didn't write down what that number is in radians. All right. I'm gonna. So you if I go through this, I'm gonna get a number in radians here. All right, and I probably should just do that calculation real quick on the fly so I have it. What is it?
0.12 pi.
All right, 0.12 pi. I take your word for that. That's radians. Now, one thing I want to be clear about, that is almost, I will never probably ask for you to give me that angle in radians, okay? If you say you go work at Duke one day, right, and you might see that the voltage at a particular point in Duke's network has a particular amplitude and a particular angle. That those things are really important, the angle and the amplitude. You'll never hear an engineer at Duke talk about how many radians, because I don't really have a very good sense of what 0.12 pi radians really looks like. If you told me what angle is that, I don't really know exactly what that would be. So typically we do that in degrees, all right? How do I convert that to degrees?
0.12 divided by pi times 180.
Yeah, divided by, so yeah, if I wanted to convert this guy to degrees, I would say pi 180 over pi, right? And I would work that out to, in this particular case, to be 21.6 degrees. All right, and we're going to put that, maybe fit it down here, 21.6 degrees, okay? Now, one thing that's really important here, since it lags, what do I put in for phi? Do I say that phi is equal to 21.6 degrees?
Negative 21.6 degrees.
Negative, yeah. So basically, I'm going to put a negative sign here throughout now. So this guy is equal to negative 21.6 degrees, okay? So that means this waveform here is 10 cosine 100 pi t minus 21.6 degrees, like that. All right. And, you know, like I said, you'll never ever see any engineers, any real engineers using radians per second. Well, using radians for angles. Okay. You'll always see them use degrees.
Is 100 pi not in radians?
So 100 pi is radians per second. All right.
Oh,
So
we
that
need to change
actually,
it,
that's actually a good point. So if you went into, let's say you go into MATLAB and you write 100 pi t minus 21.6. One thing to be careful about is if I multiply out 100 pi t, I get an angle in radians. 21.6 is an angle in degrees. I got a mixed set of units there, okay? So typically, you know, so you got to be careful about that. If I go into a tool like MATLAB, then I got to say, well, I would actually put in 100 pi t minus 0.12 pi radians. All right. So that gets confusing for people. All right. So if I typically, and you got to be careful about this, because if you went into your calculator and you said, well, I want to put in cosine 100 pi t, and you want to evaluate it at 1 second, and your calculator is in degree mode, you're gonna be all kinds of screwed up. All right. So, you know, in general, we're not going to be dealing with things in the quote unquote time domain like I have right here. All right, but we'll see some examples of that as we go through.
The question they just popped into the chat is kind of like, I think the question I have too. How is 100 pi 3/4 radians per second? Or is that, oh, that's 314?
Yes, 314.
Oh, that's 314.
Yeah.
Oh,
Yeah.
I'm with you, bro. I'm with you in the chat. I was like, that's 3/4. I was like, how do you get that?
No,
but it's
314. Yeah.
Okay.
All right. All right. All right. So let's look at sort of a circuit here. So in this case, what I've got is, I simulated this, and what I have is a circuit. The circuit itself, the simulation maybe is a little tricky to follow, but basically what I have is this guy here. All right. Vn is the voltage source, and I have R1 and R2. So basically I have a voltage divider. Okay. I'm going to call this voltage here, V out. All right. And V in is 10 sine 2 pi 100t. Okay. So if I gave you that circuit and I said, all right, let's figure out this is V in and this is V out. Let's say I didn't tell you anything about that was an AC source. Let's just say I told you V in was a voltage source. Then how would you solve this problem? If I gave you that circuit.
Voltage divider?
Voltage divider, right? So I would say V out is equal to what times V in?
V out equals to V in times R2 over R1 plus R2.
Yep. And if you don't know what that is, again, the way, if you don't remember that, you know, it's not a big deal to remember that. The way I think of it is, what is it? It's V in divided by R1 plus R2. What is V in divided by R1 plus R2? What quantity is that?
REQ.
V in divided by that REQ. What is that?
It'd be the current.
The current.
This is I of T. That's the current, right? If I multiply that by R2,
Get the
that's the
voltage.
voltage, right? So that's the way I think about a voltage divider, you know, so that way I don't have to remember anything beyond what I already know. Okay. So what does that mean? I mean, that basically means, okay, if I take those values here, so let's say, what values do I have? I have a 4 ohm resistor. So R1 is 4 ohms. R2 is 2 ohms. Okay. So R1 is 4. R2 is 2 ohms. Okay. And I said that V in is equal to 10 sine 2 pi 100t. Okay. So basically what that says for me here is I have R2 is 2. So I basically have 2/6. If I do the math, right? 2 plus 4, and this is 2. So that says V out is 2/6 of 10 times sine 2 pi 100t. You guys follow how I plugged in numbers and just got to that?
Mm-hmm.
All right, so that says that, you know, what does this guy look like? Well, he looks like 26. So I think that's, what is that? 1/3 times 10, right? So that's 10 thirds, right? 10 thirds sine 2 pi 100t. Okay. So if I look at that and I actually plotted this guy out, so this here is my original V in. And then my V out is this guy, right? So all I see basically is a relatively unexciting result that I have right here. But if I look at that result, what do I see about V out and V in? Describe the relationships there.
It's
Yeah, it's
damped.
I would call it damped. That's I see what you're trying to say. It's smaller, right?
Yeah.
Damped is sort of a term that we use to refer to that sort of decaying sine wave idea here.
It's like it's been scaled down.
It's been scaled down. That's a great way of saying it, right? It's been attenuated is a term that we'll begin to use later, right? So this guy I'm going to say is 3.33 sine 2 pi 100t. So he's been attenuated or scaled down. So he's smaller than the input. One thing that's pretty clear though is he has the same frequency, right?
Yes.
And he's not shifted. He has the same phase. It was a sine wave. V in was a sine wave. V out is a sine wave. The current is the same way. It has the same frequency. All the timing is the same. So that, you know, I said V in divided by 6, right? We kind of did that here. V in divided by 6. This guy is the same as well. So essentially this guy, if I do the math on that, this becomes 1.67 sine 2 pi 100t. So if you look at that for a second, right, that kind of gives me one sort of important result right off the bat, doesn't it? How can I simplify all of the work that I just did in this circuit? Not to say that I did a lot of hard work, but I could simplify the work a little bit.
Do anything with the magnitude only. Don't need.
Yeah, only the amplitude changed. In other words, it looks like I didn't even need to include the sine, right? The frequency didn't change. Everything is a sine wave, right? So basically, I see something interesting about that right now is I can make my equations a lot easier right? If I did the math and said, well, V in had 10 volts as its amplitude, V out would have 3.333 volts as its amplitude. The current has 1.667 as its amplitude, right? And essentially, the only thing that's changing as I go through that circuit, everything has sine 2 pi 100t in the expression, right? There's nothing fancy about it. The currents, the voltages all have sine 2 pi 100t. The only thing that can change as I go through this is the amplitude, all right? That's important. So this I call this guy a sort of a static circuit, or a circuit with only resistors, okay? Now those are pretty boring circuits, but we have one important result that we see, right? Which is to say that only the amplitudes changed, okay? What's going to happen if I include capacitors and inductors? Any ideas?
It's gonna shift and the angular is gonna change.
It's going to shift, but the frequency will never change. All right. The frequency never changes. The frequency is always the same, which is what we'll see as we go through the rest here. So let's take a look at this guy. All right. So in this case, I've got a circuit very similar, right? I replaced one of the resistors with a capacitor. Okay. So in this case, let me just to draw it. My source here is this guy is cosine 2 pi ft, and I specifically left it as 2 pi ft. I'm going to change f as I go through this. This guy is R, this guy is C, and my values of R and C are over here, okay? So here's V out, the voltage across that capacitor. All right, now, if I gave you that problem based on what you know already about circuits, how would I figure out V out?
Would you create a first order circuit
Yep.
or equation?
Yeah, do a first order differential equation, right? So I've got, all right, I'm going to call this Vn of t. And this guy is going to be cosine 2 pi ft. And I have R and I have C. All right, and this is V out across here. All right, so how would I figure out the differential equation that'll tell me V out? What's my tool here?
KVL.
KVL, right? So I'm going to put pluses and minus here. So I'm going to say I'm going to go around this guy in a clockwise direction. So I go from minus to plus on my Vn. So I'm going to say minus Vn, and then I'm going to go plus to minus on this. And I'm going to say the current is defined going that way. Okay. So I'm going to say I've got IC times R plus V out, the voltage on the capacitor. Now, how do I turn that into, I can bring the Vn over. So Vn cosine 2 pi ft is equal to ICR plus V out. How do I turn that into just a straight differential equation for V out? What else do I need to know?
IC equal to dVc over dt.
IC equals C dVc dt. So in this case, I've called the capacitor voltage V out, right? So I'll say it's that. So now I have RC dV out by dt. That is what I would call a differential equation, okay? All right, so I've got Vn of t, right? Because now it's a function of time, cosine 2 pi ft equals RC dV out by dt plus V out. Okay, now, what is the solution to that? What's the solution to that? First of all, it's a differential equation, and I can do Laplace transforms, a lot of ways to solve a differential equation, right? This is not as simple as if I had a DC source. But if I had a DC source, right, if this had just been 5 volts equals RC dV out plus V out, right? If I just had 5 volts, a constant, what would we say that we have? What would be the general form of that solution? we would say that we have two parts to it, right? What would the two parts be?
Homogeneous and particular?
Homogeneous in particular, okay. What's the form of the homogeneous always? What form?
It,
Steady state.
No, the
No.
homogeneous is my transient solution. What form does that
That's-
always have?
That's V cosine.
No.
it's just it's
Exponential.
first order differential, right?
So it's a first order differential equation. So it has a homogeneous, which is the transient response. What form does the transient response always have?
Exponential.
E to the ST.
Exponential, right? So this guy would be a e to the negative t over tau. And the tau in this case, if you go back and compare it to our general form, tau is RC. Okay. This guy is my homogeneous or transient response. What's that mean, the word transient in this case? What's going to happen to that thing?
It's when we analyze it in 0 plus. It's like how, or it increases exponentially in transient.
Goes to 0.
What? Oh, it goes to 0, right? The transient always decreases exponentially. It better never increase exponentially. If it
Okay.
does, you did something wrong, right? It's impossible to have that happen, right? A e to the negative t over tau plus he's going to have a steady state solution, right? What's the general form of the steady state solution to this? So in other words, there's a couple of ways you'll learn how to do this in differential equations, right? One is Laplace transforms, which will give you the same result. The other would be that you would guess a steady state solution of a particular form. All right. And then you would figure out what the coefficients are in that steady state solution. Okay. What is the form of the steady state solution? Now, don't get too lost in the math. What do you think it's going to look like? If I put a cosine into this circuit, right? If I had a circuit with resistors, just purely resistors, right? And I put a sine wave into that circuit. So V in went into a circuit with purely resistors. Then all the voltages looked the same, didn't they?
Yeah.
What do you think? What do you think
So
it's
it-
going to look like in this case?
It would just
You'll
be
get a
coefficient
cosine?
with a cosine.
Yep. And it's going to have some unknown amplitude. And it might be shifted. This guy here is my steady state. Meaning once the transient's dead and I just sit there looking at it forever and it reaches steady state, meaning the steady state means the transient's gone, right? Steady state or particular solution. All right. And if I look here, what I did was I changed the frequency, all right, a couple of different ways. So I first said, all right, well, let's start out with the frequency equal to 0.1 hertz. All right, and I did that for the RC values that are included here, 15.9 kilo ohms and 1 microfarad, okay? 1 microfarad means how many farads?
1 e to the negative 6.
1 e to the negative 6, okay? So some of the problems you guys get in class or in the homework, you have a 1 farad capacitor. No one ever has a 1 farad capacitor, all right? 1 microfarad is a pretty big capacitor, all right? Unfortunately, you know, farads were kind of improperly sized back in the day when they first came up with them, right? So you'll see a lot of numbers like that, 1 microfarad. So it's 10 to the minus 6. So that's important to remember. All right. So for that particular circuit, if I look at what V out looks like, what I see is the input V in is in blue. All right. I can't even really see the blue waveform, right? Looks like the blue and the red are sort of right on top of each other. Right. And what I can see here is, so you can see a little bit, if I zoom in right there, you can see that there's some difference between the input and the output. Okay. The output being the voltage across this capacitor. So right here, this guy right here, what I've highlighted in this red box, that's the transient response. And then what I see is essentially the steady state solution looks almost exactly like the input voltage. Okay. Now what I'm going to do is I'm going to increase that frequency. I'm going to, instead of having it be 0.1 hertz, I'm going to take it to 10 hertz. Okay. Now, what do you notice here? So now I can see the transient a little bit. The transient kind of makes the first couple of periods look a little bit weird, but then eventually the transient's gone. Because remember, our solution is a e to the negative t over tau plus some unknown value cosine omega t plus phi. All right. Looking at this here, a e to the negative t over tau eventually always becomes equal to what?
0.
Yeah. And so what I'm sort of saying here is I can see that transient for a little while, but then eventually this guy becomes 0, right? If I wait long enough. My x-axis here is time. So by the time I'm out in this region that I've identified here as the steady state, that exponential is gone. And if this circuit is turned on for seconds or minutes or something like that, typically what we say is we stop caring about the transient response. We don't want to solve differential equations all the damn time, right? Solving differential equations is, pardon my French here, but it's a pain in the ass, right? In general, to solve a differential equation, right? And so we don't, and usually it lasts, like in this case, how long does the transient last? Well, it lasts 0.1 seconds. If this circuit is turned on for days, that transient response is a very small percentage of the overall time that I might be looking at that voltage. So when I look at this, what this sort of says is, if I want to characterize what's going on in steady state, it looks like the amplitude has changed, right? In this case, the output voltage is smaller, right? And it's also shifted, right? Is this guy shifted to the left or to the right?
To the right.
To the right.
To the right. Okay, so that means that it's
Lagging.
leading or lagging?
Lagging.
Lagging, right? He has his peak at a later time, all right? Now, let me ask you this. What do you think is going to happen if I increase the frequency to an even higher value? Like
The
100
lag will
hertz?
be more notable.
The lag will be more noticeable if I go to a higher frequency. And what do you think is going to happen to the amplitude? So here it was at 0.1 hertz. They had the same amplitude.
Keep decreasing.
Yeah, at 10 hertz, it's smaller. If I go and I look at 1,000 hertz, now it almost looks like I can hardly see the output, right? It's shifted, but it's much, much smaller for sure, right? So it's more shifted and it's smaller. So basically, if I kind of summarize what's happening here, is that if I look at different frequencies, what I see is, one thing that's important too, does the frequency of the output ever differ from the frequency of the input?
No.
Never. And it never will, right? The frequency, if I look at any circuit with R's, L's, and C's, if I put in a cosine source, then what I'm going to see is cosine outputs. They might be shifted, they might be scaled up and down, they might be shifted left and right, but they'll never be at a different frequency, all right? Frequencies will never change. Phase shifts might happen, amplitude shifts might happen, right? But I'm never going to see any kind of a change in frequency. The timing will always be the same. All right. The other important thing it seems like here is frequency also seemed to be important, right? As the frequency changed, what I got out changed. So that's important, right? It tells me frequency must be kind of important in telling me how much shift and how much scaling happens, right? But it doesn't change itself. All right. And that's kind of an important thing for us to remember here. But one thing that's kind of important to see is when I look at this, the only thing that's happening to that voltage as I change that frequency, there's always going to be a transient response. Okay. Transient response is always there. But if I look at the steady state solution, the only thing that's changing is that scaling, this B factor, and this shifting phi. So that tells me that I actually can ultimately forget about keeping the cosine around, and I can get rid of it and I can deal with it later. Okay. And that's what we do typically when we do our analysis, right? So we're gonna come back to what I was talking about there. But if I'm gonna make use of that concept a little bit, this idea of something we call a phasor. All right. So when I think about a cosine wave with that general form, x cosine omega t plus phi, right? I say this is my general form of a cosine wave. I say there's basically, to be able to draw it, there's 3 parameters that I need. I need to know something about the frequency or the timing of it. I need to know the phase shift, and I need to know the amplitude, okay? If I know those things, I can always draw the waveform as a function of time, all right? How many points are on that waveform that's drawn right here? So here's this waveform. Ideally, you know, how many, if t is on the x-axis here, how many points are drawn there?
Isn't there infinitely many points?
Infinitely many points. But if you think about it, there's like a compression thing that sort of happens. If I know omega and I know phi and I know x here, I can always draw the waveform for all values of t, can't I?
Yeah.
I could just plug in the numbers, right? So I think of this as like compression, right? I can basically say, you know what, I don't need to know what's happening at every given time, because the only things that happen as I go through a circuit are I change the phase and I change the amplitude. And so we can actually just track what happens to those two things and forget the time stuff, right? That makes things a lot simpler. That means if I don't need to track the time, ultimately it means I don't need to do differential equations, all right? And it gets differential equations out of the picture, all right? That's what's really important for us, okay? So to do that, I need to make use of this concept called a phasor, all right? So essentially what we do is we say, I am going to define a phasor. If I'm given a waveform, so in this case, I was given this guy here. X of t is 10 cosine 2 pi 10t plus 45 degrees. All right, essentially what we do is we make a complex number called a phasor. And we say, so it's a complex number. So you guys are in 2254 right now. Yahoo's already done complex numbers?
Yeah.
Yeah, we're on it.
Okay. All right. So in this case, I'm going to say, all right, this complex number here, 10 cosine 2 pi 10t plus 45 degrees. I'm going to express the phasor of that guy like this. It's the magnitude or amplitude with an angle of phi. So in this case, for this particular waveform, I'm going to say that I have 10 with an angle of 45 degrees. Okay. Now it's a complex number, so that means I can draw it in the complex plane. So where would I draw 10 angle 45 degrees in my complex plane that I've drawn here?
On the first quadrant?
First quadrant, right? This is the real, and this is the imaginary. So you guys, this is not new to you guys. So here's 45 degrees. And this is what I would call X. So typically I write these phasors with a bar underneath of them, all right? And I could express this guy as having a real part and an imaginary part, right? So I could say X here, which is 10 cosine, 10 angle 45 degrees. I could say this guy has a real part and an imaginary part, right? What would those be?
Well, you can just say X and Y using R cosine theta and Y equals
so what would the
R
real
sine
part
D
be?
theta.
Yeah, 10 cosine
Cosine
45.
45.
Yeah. And we could work out what those are. And then I would say plus J times 10 sine 45. And Yahoo has introduced J, right? Not I.
Yeah. Correct.
All right. Yeah. So this is where so why are you learning complex numbers over there? Because essentially, what we're going to see is we're going to do something weird. Okay. We're going to start using imaginary numbers. Everybody says, why we use imaginary numbers? They're imaginary. Well, they are, right? They're imaginary, but they stand for something. What they do is they allow us to express the phase change and the amplitude change that happens in a circuit. And that's why we use it. Essentially, we have two options. When I'm faced with circuits that have R's, L's, and C's, and I have AC sources, and we said at the very beginning, AC sources are really common. If I have circuits with AC sources and R's, L's, and C's, I got no choice but to solve differential equations out the wazoo, and that's really annoying. And none of you would want to be electrical engineers if that was the case. If you had to solve differential equations all the time, you wouldn't want to do it. What we found, what somebody discovered over time was basically, well, I can try, if I know with this really fundamental result, this is why I want to say this result over here is really fundamental. If I look at any circuit with R's, L's, and C's, the only thing that happens in steady state is what two things? I've said it a
The
bunch of
amplitude,
times.
the
Amplitude.
amplitude change.
Yep.
Phase.
Phase shifted. Yeah. So if I know that those are the only two things that happen, I can just say, you know what? I want to track what happens to the quote unquote phasor of that circuit. I want to track what happens so I just pull out the amplitude and the angle. And I'm going to just track those. All right. Now we're going to see on Wednesday how we use that information. All right. To greatly simplify and just get rid of the differential equation completely and jump ourselves into a world where we can use something different, something that is exactly like what we learned in circuits 1, which is basically, I just want to use Ohm's law. I don't want to have I equals C dV dt. I don't want V equals L di dt. I just want to have some kind of an Ohm's law relationship, which is a lot simpler. And we can do that, all right? And that's what we're going to do on Wednesday. But to be able to do that, I'm going to need to know what a phasor is, all right? So, if I gave you, let's say, so Vn was cosine 2 pi 10t. If I had that as my Vn, all right, how would I express the phasor for Vn? What would the phasor be for this guy? So he said the phasor relates the amplitude and the angle. So if I just have cosine, what's its amplitude?
1.
1, 0.
And its angle is 0 degrees. And so where would I draw that guy?
On the x-axis.
On the x-axis, and it would be here. All right, so this is V in. Okay. Now, V out, let's say, was this voltage here. So apparently this guy has 0.7044 as his amplitude and negative 47 degrees as his angle. So what would I write as the phasor for that guy?
0.7044.
Yeah, 0.7044. And what would the angle be?
Angle negative.
Negative 47 degrees. Now, where is that?
And that would be
We're somewhere down here, right?
low.
And so if I look at this, the way that I think about this, so V out in this particular case, looking at the time domain picture on the left. So this is sometimes I'm going to call this the time domain. All right, this is the real world. If I go and measure with an oscilloscope, those are the voltages that I'll see. Okay. This over here is what I call sometimes the phasor domain, and we draw this stuff in a complex plane, right? What is this angle between these two things here? It's negative 47 degrees, right? So if looking at this, look at the picture on the time domain on the left. Does the red V out, right? The output voltage V out, the red one, is that leading or lagging?
Lagging.
Lagging. All right. And so if it's lagging, it's always going to be, it's always going to be more, I don't know, I probably shouldn't touch on that today, but it's always going to be behind the other one. So this guy is negative 47, meaning he's in a negative direction. So remember, which way is the positive direction if I'm talking about angles?
Left.
Clockwise.
Clockwise, right? And the negative direction is
Counterclockwise.
sorry.
Other way around.
Other way around, yeah. So the positive direction, as I go this way, right? This is increasing angle is counterclockwise. Decreasing angle is clockwise, right?
Mhm.
So something that has a negative shift like that is said to be lagging. And we're going to deal with that kind of terminology more as we go through the semester, all right? But essentially, we should be able to kind of make, for now, our first step here today is I want to be able to make this jump from a waveform in the time domain to a phasor. All right, so let's say I've got this, we're going to pick up with this second one here on Wednesday, but let's say I have 10 cosine 2 pi 60t minus 90 degrees. What's that guy going to be? What's the phasor for this?
10
It's
angle
10
angle negative 90.
Negative 90.
Yeah.
Now, what is it for 5 sine 2 pi 30t plus 30 degrees?
It would be 5.
5 angle 120.
Okay, this is where it gets tricky, right? So if it's sine, I always have to convert that to a cosine. Okay, so let's deal with that one. So some people might have looked at that and said 5 angle 30 degrees. All right, that's not right. I have to convert sine to a cosine, and I can do that. All right, and we're going to do that on Wednesday. All right, I'm going to stop there for today. But I want to make sure the key takeaways for today and our understanding is that we're going to make this jump and figure out how we can relate a time domain waveform to a phasor. And the other really important thing for you guys to understand and walk away with here today is if I have essentially a circuit like what I showed here, right? I've got a voltage source and any combination of resistors and capacitors and inductors. The only thing that's going to happen if I look at the voltages and the currents in that circuit, there's going to be a transient response. What happens to the transient response always?
It will always decay to 0.
Always decays to 0. And what about the steady state response? What are the two things that are always true about
Always
the
goes
steady
to
state?
infinity.
No, the phase shift and the amplitude.
The phase shift and the amplitude change, right? The phase shift. So it's potentially got a different amplitude than the input, and it's a different angle than the input. But that's it, right? And we saw that here. And basically, as frequency changed, that relationship between amplitude and phase was different at each of those different frequencies. But the fact that it's simplified to just those two changes means that I can get rid of differential equations. And that's what we're going to talk about on Wednesday. All right, that's it for today. All right,
Thank you.
I'll hang out here for a couple.